Myself, Dr. K. Viswanath Allamraju, Institute of Aeronautical Engineering, Department of Mechanical Engineering, Dundigal, Hyderabad. In this session, we are going to study the revision of bending stress distribution. The course outcome Bloom's taxonomy. Course outcome and Bloom's taxonomy for this session is apply the knowledge of theories of failure, shear force, and bending moment relations for analyzing the flexural stress, shear stress distributions, and failure of beam sections. And Bloom taxonomy level related to apply level, because this is a problem based topic, so we have to remember the concepts, understand them, and apply. So that's why this topic is belongs to the level of apply level. In this revision here, let us begin what is stresses, bending stresses. Bending stresses, or what is bending stress distribution? Bending stress distribution. In this session, that bending stress distribution, to the variation of we study or we find out or we calculate the bending stress across the cross section of a beam, how the bending stress is varied along across the section of the beam, cross section of the beam when the load is applied. So in this bending stress, in order to analyze the bending stress analysis, we have to first understand the concept of pure bending. And what is the theory of pure bending? So what is the pure bending, concept of pure bending? If we consider a overhanging beam having a point load at the free ends at the distance of A from the left support and to the right support, and the distance between two supports is L. If you draw a shear force and bending moment diagram, one side of the shear force and another side of the shear force, the shear force will be, but this is the shear force diagram, and draw a bending moment diagram. The bending moment varies up to the support A, and from left side load to A here, and right side to up to support to B varies. But here the bending moment curve, you can see it is a constant. And if you observe in the shear force, this is the bending moment diagram. The shear force is 0 at the span of L, length L. The shear force is equal to 0 here, but the bending moment is constant. It doesn't vary. This phenomenon, or the portion between A and B, experiences pure bending. There is no shear force. So the bending moment constant and no shear force. This phenomenon is known as a pure bending. So pure bending means when the load is applied on a beam, the portion of the beam experiences bending, constant bending moment, and the shear force equal to 0. Then it is known as the pure bending. And what is the application of pure bending? The application of the pure bending is that when weightlifters lifts the bus barrel, and carries. The person exactly supports the hands at these points and carries. So this portion here, between two hands holding points A, B, the portion of this bus barrel experiences constant bending moment or experiences pure bending. There is no shear force. The equal weights W and W keeps the hands at exactly position at the distance of A both the sides. So here it is like two supports. It's like a overhanging beam phenomena. The portion between A and B is 0 here. AB experiences. The portion between A and B experiences a constant bending moment and shear force is 0. So what is the next theory of simple bending or theory of pure bending? Theory of pure bending. Theory of pure bending is that is M by I equal to sigma by Y equal to E by R. This is the equation comes from the theory of pure bending. So here when the beam experiences, here the load is applied on a overhanging beam, the beam experiences bending moment, that is W into A. The bending moment causes, the bending moment, another name is called moment resistance. The moment resistance leads to the bending stress and also radius of curvature happens because of the bending load, and this bending load also acting on the beam, that means beam section effects, that means moment of inertia, area moment of inertia. So this area moment of inertia and moment resistance that takes place, it is internal resistance, that means across the section of the beam. That's why the distance from neutral axis, that is the Y. And also when the moment resistance, in order to increase the moment resistance, or in order to increase the bending stress will be increased when the distance from neutral axis to the topmost fiber, to the distance of the fiber layer increases. So when it is increasing, so it affects, that means the property of the material. The property of the material means that modulus of elasticity come into the picture. That's why in the theory of pure bending, these are the parameters or these are the properties comes. There is the moment resistance where M is bending moment or moment resistance. The unit for bending moment is Newton millimeter, and I is area moment of inertia or second moment of area. Area moment of inertia, that is millimeter per 4, and sigma is bending stress. Bending stress, that is Newton per millimeter square. Where Y is distance from neutral axis. Distance from neutral axis to the fibers, where E is modulus of elasticity. The unit for E, that is also Newton per square millimeter, where R is radius of curvature. It is in millimeters. Based on the data, we consider the relation between two equations, that is m by I or sigma by y. Suppose in the problem, if it is given the data about geometry and the moment of resistance and the distance from neutral axis, and we have to find out the bending stress, the maximum bending stress, then we have to use these two relations. And if the data is given, moment of resistance and the geometry, from the geometry we'll calculate the second moment of area and modulus of velocity, and we have to find out unknown. Then we have to use m by I and E by R. So the principle is that based on the data we have to use these relations. The theory of simple bending, what is the importance of pure bending? This theory of pure bending is highly useful in order to find out the shear stress distribution across the sections of the beam. And also, the theory of pure bending also useful in calculating the deflection of the beams when the load is applied. So for understanding the pure bending, you should have the knowledge of bending moment calculations. That is the topic in shear force and bending moment diagrams. So when we have the knowledge of shear force and bending moment diagrams, then bending stress distribution can be understood easily. When we have the knowledge of bending stresses distribution across the sections of the beam, the shear stress distribution can be calculated. After understanding of shear force and bending moment diagrams, bending stress distributions and the shear stress distributions, then we can calculate the deflections and slope of the beams for various types of beams, such as cantilever beam, simply supported beam, overhanging beam, and fixed beams. Now, what are the assumptions in this theory of pure bending? The assumptions considered in this theory of pure bending is that one of the main assumptions is that it is isotropic, the material should be. And second assumption is that the modulus of elasticity remains the same both in tension and compression. So when the beam is applied here, suppose when the beam bend upward direction or downward direction after applying the load, the beam will bend. So the top layers of the beam experiences compression stresses and the bottom layer of the beam experiences tensile stresses. There is a tensile deformation and the compressive. Okay, and these are the important things. Coming to, in order to calculate the bending stresses or moment of resistance of various sections, in nature, mainly there are two types of sections. Number one, symmetrical sections, and number two, unsymmetrical sections. Symmetrical section means here it is single symmetric or double symmetric. If the geometry is, if the section is symmetry about both x-axis and y-axis, it is a double symmetric. And on some of the sections are symmetrical about either x-axis or y-axis. Those are considered as single symmetric sections. In this figure, we can see the double symmetric rectangle. Rectangle is a double symmetric, and I section is also double symmetric, and whereas channel section, here it is, the channel section is single symmetric, it is symmetric about x-axis, and T section is considered as single section, single symmetric, it is symmetric about y-axis. And if you consider some of the sections, those are unsymmetrical sections. Here considered I section, it is unsymmetrical about x-axis and symmetrical about y-axis. Here the T section is symmetrical about y-axis and unsymmetrical about x-axis. Whereas inverted U section, it is symmetrical about axis y but unsymmetrical about horizontal neutral axis, that is axis x. So these are all comes under unsymmetrical sections. Why we are considered here unsymmetrical sections? These sections are not symmetrical about axis x, which is horizontal neutral axis. So in this case, we are going to consider if the section of the beam is a T section, that means it is unsymmetrical about when the load is applied on that beam, transverse direction. So this section is unsymmetrical about axis x. So at that point, okay, we have to consider in order to find out the maximum distance from neutral axis to topmost fiber, we need to locate the neutral axis. How to locate the neutral axis? The location of the neutral axis can be done by calculating the centroid of that section. So the centroid comes from the formula of, suppose, bar y, vertical distance from neutral axis location, that is a1 y1 plus a2 y2. For it is T section, there are two areas are there, a1 plus a2. Okay, it is for section about this inverted U section. For this section, bar y equal to a1 y1 plus a2 y2 plus a3 y3 by a1 plus a2 plus a3. If you consider the I section is the section 1, section 2, section 3, the formula is that bar y equal to a1 y1 plus a2 y2 plus a3 y3 by a1 plus a2 plus a3, sum of s. With the help of the centroid, we can locate the neutral axis. So after locating the neutral axis, the distance from neutral axis to topmost layer, and that is the y maximum, and the distance from neutral axis to bottommost layer. So the largest value among these two distances we considered as the y maximum. Why we are considering y maximum? From that maximum y value comes the maximum stress value. Suppose if it is the T section of the beam, if the beam is the T section, the T section of the beam, and it is supported at both the ends, fixed at the ends. This beam is subject to a UDL. If it is subjected to UDL, then what will happen? If it is subject to UDL, uniformly distributed load, then the T section experiences the bending takes place. In this bending takes place, the bending of the T section takes place. The bending of the T section takes place. So the topmost layers in this bending, the topmost layer, this is the bending portion. This portion experiences compressive stress, whereas the bottommost layer, suppose the neutral axis. If it is the neutral axis, the bottommost layer experience sigma t, tensile stress. If the distance from neutral axis to topmost layer is yc and it is yt, if yc is greater than yt, if yc is greater than yt, that means sigma c is greater than sigma t. That means compressive stress is greater than the tensile stress value. If yc is greater than yt. So in the problems, if it is asked that we have to find out the maximum bending stress, so we have to locate the neutral axis with the help of the central distance, that is y bar y here. After locating the neutral axis, we have to find out that we have to measure the distance from neutral axis to topmost layer and neutral axis to bottommost layer. The maximum value of those two layers, among those two values, consider the maximum value, that is y maximum. From that y maximum, we can find out the sigma maximum. How to calculate that is sigma c or sigma t? How to calculate? That is m by I equal to sigma by y. Sigma equal to m by I times y. If y becomes y maximum, sigma becomes sigma maximum. This y maximum is towards the tensile bottom layer. In this case, the sigma maximum becomes tensile stress. If a y maximum value is the yc, then sigma maximum becomes a sigma c. So in that manner, the meaning of the bending stress will be changed based on the nature, behavior or nature of the material. Here the deformation is a high level in the bending when the load is applied at the top. Here the top is load applied, the bending takes place. Okay, that's why the bottom layers experiences tensile stresses and the top layer experiences compressive stresses. So which level here? The bottom layer experiencing maximum stress value or top layer experiencing maximum stress value? How can we know? With the help of the value of the y. The value of the y is maximum from neutral axis to top in comparison to from neutral axis to the value of the y from neutral axis to bottom layer. So that gives the maximum stress value. The nature of the maximum stress, it can be a tensile or it can be a compressive. So that is the meaning here. So this is the calculation or this is the concepts of using a pure bending equation, that is m over I equal to sigma over y. Now suppose if the moment resistance is maximum, that means if the moment resistance is maximum, that is m by I equal to sigma by y, where m equal to sigma times I by y. This moment of resistance is maximum means it is resistance to bend is maximum. That means how it represents, this is the I by y max. I by y max means section modulus. That means section modulus becomes maximum. Thus section modulus Z represents the strength of a section. Section modulus represents the strength of a section. What is the strength? What is the section modulus? Mathematically, it is the ratio of moment of resistance, area moment of inertia to the y maximum, that is distance from neutral axis to the topmost fibers, or maximum distance from neutral axis to fibers. So this Z represents strength of a section. Why? The moment of resistance to bending is maximum. So this bending, that means the moment of resistance is proportional to section modulus. That means moment of resistance is maximum because of Z maximum. So that Z represents the strength of the section. So when the strength of the section is high, moment of resistance is high. Thus in relation like that, so the moment of resistance is maximum because of Z is maximum value, is the section modulus concept. Now if we consider the I section, let us consider the problem. So a cast iron bracket subjected to the bending has the cross section of I from I form with unequal flanges. The top flange is not equal to bottom flange, unequal flanges. The dimensions of the section are shown in figure. Find the position of the neutral axis and the moment of inertia of the section over the neutral axis. If the maximum bending moment on the section is 40 meganewton millimeter, determine the maximum bending stress. What is the nature of the stress? What is the nature of the stress means compressive or tensile. So this a bracket is shown in figure like a cantilever applied at a free and section of the beam is I section. It is non-uniform. I form with unequal flanges. So first we have to locate the neutral axis. For that we have to use bar y, that is y bar equal to a1 y1 plus a2 y2 plus a3 y3 by a1 plus a2 plus a3. This a1 is the section 1, area of the bottom flange is the a1, this is the one, and a2 is the area of the web, and a3 is the area of top flange. So the top flange area is 10,000 millimeters, web is 10,000 and millimeters. Area of the bottom flange is 6,500 square millimeters. So after substituting a1, y1, a2, y2, a3, y3, all these values in the formula, then location of the neutral axis. The bar way is calculated as 166.51 millimeters from the bottom flange. It is 166.51. What is the distance from top flange to neutral axis? Distance from neutral axis to top flange edge. That means it is total distance, total length. That the depth is that 300 millimeters. 300 minus 166.51. So that comes under 133.49. So which portion is experiencing maximum stress? The maximum. This is the Y maximum. So for cantilever beam, when the load is applied here, the bottom it bends like that. It's completely bending. So what will happen here? The top layers experiences tensile and the bottom layer experiences compressive. So the distance from neutral axis to bottom layer, that is 166.51. So these bottom layers are experiencing maximum stress value. So in our formula, m over I equal to sigma by y. This y becomes y maximum. This is the distance. And sigma becomes what? Sigma is compressive. And one more thing. What type of nature of the stress it is experiencing? Compressive stress it is experiencing. Compressive stress. So we will calculate moment of inertia. That is from these three sections over the neutral axis. By using a parallel axis theorem, we can calculate, that is A1, I1 plus I2 plus I3, I equal to I1 plus I2 plus I3. So after calculating that, we know the I value, we know bar y, yes, and this is the formula, m by I equal to sigma y. What is sigma equal to m by I times y. So what is the distance y here? From distance from neutral axis to bottom, that is 166.51 y value. So sigma equal to m by I times y. Substitute here, that is 23.377 Newton per square millimeter. The nature of the stress here, it is compressive. So these are the textbooks we followed as a references for this session. So in this session is a glimpse of revision was done here to understand the concepts of bending stress distribution or bending stress variation across the sections of the beam. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.